In order to bound the pool size under the greedy algorithm, I'm going to just write down the differential equation of this pool size. And to do that, let's assume we are at some time t, and pool size is zt, and I want to look at the pool size at just some t plus dt time after t. So dt is very small. Now, what can happen in this dt period? Well, the arrival rate of new agents is m. So m dt new agents are going to come to the market, and then the departure rate of agents is just 1. So, and I know that with probability 1, all critical agents die. So the departure rate of each agent is 1. So the departure rate from the system is just equal to the pool size. So dt times zt agents will leave the market unmatched. They become critical and leave the market. Now, for these new agents who come to the market, many things can happen. They can either find a match or not find a match. So let's write down this differential equation in the following way. It looks a bit scary, but it's actually very, very simple. So I start with pool size zt, this first term here, and I want to calculate what is z dt plus dt. And then I have these terms here that are very simple if you look at them carefully. The first term is the rate by which some agent come to the market, which is mdt. So this is the arrival rate of new agents. And if I cannot match that new agent, then that agent is added to the pool size increases by 1. Okay, so that's quite simple. This is the probability I cannot match a new agent. This is the arrival rate of new agents. And if this happens, the pool size is increased by 1. Now, what if I can match the new agent? Well, with this rate a new agent comes, with this probability I can match a new agent, in which case the pool size decreases by 1, because now one agent in the pool is matched to this new agent and is leaving the market. And this term here, minus dtz, is simply the rate by which someone gets critical and leaves the market unmatched. And then I have some lower order terms. I have dt squared and so on and so forth, which I don't need to be worried about, because now what I'm going to do after this is to take this zt to the left hand side, divide everything by dt, and then get dt to go to 0 to write down this differential equation, the differential equation associated with the pool size. Now, I don't want to go through all these details, because once you have this equation, you can write down the differential equation. The only problem in solving that differential equation is that these terms, 1 minus d over m to power z's, are nonlinear. And solving a nonlinear differential equation is often tricky. The way I'm going to solve that differential equation is this approximation. I know that 1 minus d over m to power z is at least 1 minus zd over m. And this is going to help me to put this approximation into these equations and get this differential equation, which is now just an inequality as opposed to equality. If you solve this differential equation, you can easily show that pool size under the greedy algorithm is at least m over 2d plus 1. Now, for the patient algorithm, I'm going to use a very, very intuitive argument, which is the following. Suppose the planner does not match anyone. Well, what will happen? If I do not match any agents, agents arrive with rate m, each agent departs with rate 1, so the steady state size of the market, how many agents I have in the market, should be m, because then the departure rate, which is m, would be equal to the arrival rate, which is m. So if the planner does not match anyone, the pool size should be m. Now, my claim is that if the planner matches everyone, this is not going to be true, but suppose the planner under the patient algorithm could match everyone. Now my claim is that the pool size must be m over 2. Why? Because the arrival rate of agents is m. Now suppose the pool size is x. For any agent who becomes critical, which happens at rate x over 2, it happens at rate x, 2 agents will leave the market, because I will match a critical agent to some neighbor. As a result, for any critical agents, 2 agents will leave the market. So if the pool size is x, the rate by which agents leave the market is 2x. Now in a stationary, this 2x, the departure rate, should be equal to the arrival rate, which is m. As a result, x should be equal to m over 2. Okay, so if the planner can match all critical agents, the pool size in expectation should be m over 2. If the planner can match none of the critical agents, the pool size in expectation should be equal to m. Now this immediately tells me that because the patient algorithm will not match all agents, but will match some agents, the pool size under the patient algorithm would be somewhere between m over 2 and m. That's exactly the argument that gives you the intuition. Now, what is the exact proof? That's going to be a little bit more tricky. Now, just to review what we did, we showed that the loss is our perishing rate divided by the arrival rate. I bounded the pool sizes, and I got the losses for different algorithms. This was a relatively long proof overview. Now there are so many technical details that I'm going to do that in hopefully an appendix video, which I'm going to call appendix, because these technical details are just too much for us to go through if you are not doing research on this exact field. You probably don't want to go through all the technical details.